So I'm just gonna plow ahead, and I apologize. Hopefully the internet decides to cooperate with me this morning, but yeah, we'll see. Okay, so here's what I'm gonna do. I was gonna try to do, so Zoom has this feature where we can use what's called breakout rooms. I was gonna try that this morning, but I think trying to push the technology is a bad idea at this point. So I'm not gonna do the breakout room thing. But I would really strongly encourage you to work these problems yourself. Don't just listen to me. You should try to actually work them out yourself. So here's what we're gonna do. I'm gonna share my screen so you can see the problem here. Maybe. What happened to my screen? Let's try that again. There we go. Okay, so here's our conservation of momentum problem we're going to start off with. This is the USS Iowa. The USS Iowa was actually built during World War II and was used in every major US war between World War II and the Iraq War. It was just recently retired for like the third time, because it turns out that if you really don't like people, having the ability to park a 9 16-inch cannons anywhere on any ocean in the world is kind of handy. So what the USS Iowa was designed to do was to really, really, really mess up somebody they didn't like. So it has 9 16-inch cannons that can be fired simultaneously. So each cannon can fire a shell that weighs essentially the same amount as a car and has a muzzle velocity. So when it exits the muzzle of the cannon, it's going 762 meters per second. Okay. So it can fire 9 cars at several times the speed of sound at the same time, meaning that they will all land about the same spot at the same time, which is what you do if you really, really don't like somebody. So we can ask what happens to the Iowa when it fires its cannons. And you can actually see what I'm talking about in this picture. So if you look, right? So here's the cannons firing, right? This disturbance on the water is from the shock waves of the cannons firing off. But look down here. That disturbance in the water is not from the cannons firing off. That's from the fact that the ship just got slammed sideways through the water. So you're actually seeing a wake of the ship moving sideways through the ocean, because all 9 of these cannons fired off at the same time. Okay, that's wild, and it's fantastic. It's terrifying if you're the person that they're shooting these cannons at. So what I want to do is we want to use conservation of momentum to figure out how fast the Iowa got shoved sideways. And we can do that because if we look at this system, right, we have a system of 9 projectiles and the USS Iowa. And so the only place those projectiles can get momentum from is from the ship, right? Now the ship can get momentum from a lot of places because the ship is touching the water. The ship is, you've got gravity, you've got all this stuff. But if they fired the projectiles roughly sideways, which they did, the only place to get that momentum from is the ship itself. Now, the ship didn't have any momentum to start, but that's okay because momentum is a vector. So you can always get some by just taking it from making something else move the other way. Okay? This is also a great example because this obviously does not conserve mechanical energy, right? We have no kinetic energy beforehand. We have a lot of kinetic energy afterwards. but it does conserve momentum. Okay, so let's figure out how it conserves momentum. Here's what I'm going to do. I am going to drop the link to the presentation in the chat. So if you want to, you can pull it up and see the problem while we're working on it. How's the internet connection doing?
It's doing better.
We holding out so far? All right. We'll keep hoping. Okay, so here's what I'm going to do. I'm going to come over here. There we go. All right. So what we've got here is a system that will conserve momentum as long as we think about all of the pieces of it, right? So basically what we have is 9 projectiles. Let's see, 1, 2, 3, 4, 8, 9. And we've got a big battleship. That's the USS Iowa. My artistry is beautiful. Okay, and each one of these projectiles, we know how much momentum it has, right? It has, because we know its mass. Each one of them has a mass of 1,225 kilograms, right? There's the mass of the projectiles. And they have a velocity of 762 meters per second, okay? And there's 9 of them, right? That means that the Iowa has to have momentum going this way. We know the mass of the Iowa, right? The mass of the Iowa is 4.08 times 10 to the 7th kilograms, right? Just a big number. And we don't know the velocity of the Iowa, right? That's the thing we don't know. But this is a conservation of momentum problem because the force that made these projectiles have their momentum has to be countered by a force on the Iowa backwards, right? It's the recoil. If you shoot a gun, you feel a kick backwards. That's the recoil. Okay, so that's the conservation of momentum. So if we write out conservation of momentum here, right, our conservation of momentum simply says that all the momentum we had before, initially, our momentum was 0, right? Our total momentum was 0. At the end, after we shoot the guns, our final momentum is 9 times the momentum of our projectiles minus the momentum of the Iowa, right? Actually, I'm going to write it as plus because I'm writing them as vectors. Oh, and that's equal to our total momentum, right? Now, conservation of momentum says that initial and final momentum have to be the same. Now, to use that, we have to figure out, are there any other forces that are going to change the momentum of these objects? And the answer here is yes, right? The water is going to change the momentum of the Iowa, and the air is going to change the momentum of the projectiles. Gravity is going to change the momentum of the projectiles, right? There's a lot of things happening here. But for the amount of time we're talking about here, the amount of force being applied by, say, air resistance or the water or gravity is tiny compared to the amount of force being applied by the cannons, right? So approximately, we can say that our P total initial and our P total final have to be the same, which means that when we write this thing out, we get 0 equals 9 times the momentum of our projectiles plus the momentum of the ship. Okay. So now if we plug in numbers, right, we can come over here and we can say that 0 is 9 times the mass of the projectile times the velocity of the projectile plus the mass of the Iowa times the velocity of the Iowa. We need to solve for the velocity of the Iowa, and if we do that, we get that the velocity of the Iowa is 9 times the mass of the projectiles times the velocity of the projectiles divided by the mass of the Iowa. And if we plug in some numbers here, right, ballpark, what we've got here is 10, well, I'll do approximately, 10, right, 9 is pretty close to 10, times, this is pretty close to 1,000, the mass, and the velocity is also pretty close to 1,000. Divided by, I'm going to call that pretty close to, we're just going to round it down. That's 10 to the 7th, okay? So what I've got here is 10 times 1,000 times 1,000, which is 10 to the 1, 2, 3, 4, 5, 6, 7, divided by 10 to the 7th, or approximately 1 meter per second. So to launch those 9 car-sized projectiles, the Iowa had to get jerked backwards at roughly 1 meter per second. Now we could obviously put in the real numbers and throw this into Google and do the actual calculation, right? And if you do that, you get that it's about half of a meter per second. But it's really close. It's basically a meter per second of force, of velocity that the whole ship gets going backwards. Okay? So how did we do this? Let's take a step back and talk about the problem itself. Okay? The thing to realize here was that we had a chance to use conservation of momentum. So we didn't have to worry about the acceleration or the force or any of that stuff on these projectiles. All we had to do was recognize that these 9 projectiles had momentum one way, and so the Iowa had to have momentum the other way. Now, the safety check you should always do here is ask, did we ignore anything that could have changed the momentum of the whole system? The system being the projectiles and the battleship, okay? And the answer is yes, but not very much, because gravity and the force of the water and the force of the air are small compared to what happened to the projectiles, right? The force that actually launched those projectiles, okay? Now, if you want to do a more careful job, you were really wanting to get this right, you would have to worry about those things. In this case, we're okay with just saying, yeah, it's pretty close, okay? And then all we had to do was write out our initial momentum and our final momentum, set them equal to each other, and solve. Now, you'll notice I missed one thing here. I missed a negative sign, right? I should have had a negative sign everywhere. That negative sign simply means if the projectiles are moving in a positive direction, the Iowa is moving in a negative direction, right? Opposite directions. That's all the negative sign's telling us. Okay, questions?
I don't know if it's just me, but it's hard to see. Your screen is so small for some reason.
Yeah, unfortunately, that's because of that's a bandwidth thing. You may have to go back through and look at this on the video, because the video should have the full resolution. But I'm sorry about that. My internet is apparently not cooperating today. Any other questions? It's hard to have questions if you can't see anything, I suppose. All right, let's do another one of these. Let's come back over here. share that screen. And we'll do another one. Okay, so if you play baseball, you know that when you're taught to hit a ball, the coach always emphasizes to follow through, right? Swing through the pitch. It turns out that that is good psychological advice, but it's actually useless physical advice. Because effectively, you don't matter in the collision between the bat and the ball, right? The collision between the bat and the ball happens so fast that the bat doesn't really have time to interact with your hands during the collision between the bat and the ball, okay? Now, the reason your coach has always told you to do that was because if you didn't follow through, you would stop before you hit the ball. You can't, your body is not effective at stopping the instant the bat hits the ball. So you want to keep, your coach was right from a coaching perspective. Telling you to swing through the ball was the better way to hit it. But from physics standpoint, the collision between the bat and the ball basically happens as if nobody was holding the bat. Okay? So a bat has a mass of almost a kilogram and it's moving horizontally at a speed of 33 meters per second. The ball with a mass of 0.14 kilograms was moving horizontally at the same speed prior to the collision. After the collision, the ball is moving at 49 meters per second at an angle of 18 degrees above the horizontal. Find the velocity of the bat. Okay? So this is also a conservation of momentum problem. So to do this, what we're going to need to do is sort out where the momentum is before the interaction, where the momentum is after the interaction. Okay, now, first thing we should always do with conservation of momentum problems, we should think about the other forces that are acting on these things, right? In this case, the bat also has a force from you holding it, right? The batter. And it also has a force from the air. And it also has a force from, or the ball also has a force from the air. And both of them have a force due to gravity. But it turns out that all of these forces are very, very small compared to the force between the ball and the bat, right? The ball and the bat, when they're interacting, which is very short, have a very, very strong interaction between each other. Okay, so let's work this thing out. If I come over here now, and we get ourselves a fresh sheet of paper, what we're going to find is, first thing to do is draw it, right? So we've got a before and we've got an after. So beforehand, we have the ball going this way and we have the bat. I don't know how to draw a bat. Sure, that's a bat. Going this way, right? And they're both moving in a purely horizontal direction, okay? So we know the mass of the ball is 0.14 kilograms. The mass of the bat, I can't use B again. Let's use T for bat, okay, is 0.96 kilograms. And the velocity of the ball is 33 meters per second. So there's the velocity of the ball, right? And that means the bat is actually moving with the negative velocity, right? Because it's moving the other way. Okay, now, if I were to think about this in terms of energy, right? the energy goes all over the place here, right? Energy in this collision is going to go into deforming the ball. It's going to go into making that lovely crack that you hear, right? When a batter hits a ball well, there's that kind of beautiful cracking sound, right? It's going to go into all kinds of things, heating up the bat, deforming the bat, deforming the ball, heating up the ball, making the sound. But remember, momentum doesn't care about any of that. Momentum only cares about moving objects, right? So afterwards, after the collision, right, the ball is moving the other way at an angle of 18 degrees, okay? So our theta here is 18 degrees, okay? And our velocity, which I'm going to write for afterwards, I'm going to write those as u's, okay? So the velocity of the bat or the ball is 49 meters per second, right? And that's the speed, right? So that's the magnitude of the velocity. We'll have to do some trig there, okay? And my bat, which I drew so beautifully before, which is like a club, right, has to be moving somewhere else, okay? So it has to have some velocity. And I don't know what it is, but I can guess, right? I can guess it's probably still moving forward. And I can also guess that because the ball's moving up, maybe the bat's moving down a little bit. So I'm going to draw it this way. And if I'm wrong, that's okay. It turns out if I'm wrong, I'll just get negative numbers, right? Okay. And we don't know the speed of the bat, right? Okay, this is a conservation of momentum problem. So all we have to do is write momentum before, right? So our momentum before was the momentum of the ball initially plus the momentum of the bat initially. And then afterwards, we've got the momentum of the ball at the end plus the momentum of the bat at the end. Okay, now we're going to have to be careful here because now we're going to have to break this thing up into components. Okay? We're going to have to break this up into the x and y components because momentum is a vector. Momentum cares about direction. So we're going to have to think about the x and y components of direction here, right? So let's do that. If I come over here, I'm doing the thing I tell you never to do on homework, but since we're not doing written homework anymore, I'm going to do it anyway. Okay, so we're going to have an x component and we're going to have a y component. Okay, the x component of momentum, initially, we've got the bat, right, which is just all of it. Mass of the bat, v bat, minus, because it's going backwards. Well, okay, I actually wrote this as negative, so I won't do the minus. Plus mass of the bat, velocity of the bat. And then at the end, I've got some component of the momentum of the ball, right? So let's do ourselves a favor and figure that out, okay? I'm going to write this as UBX and UBY, right? The x component is just going to be cosine. So that's just going to be UB cosine of my angle. And this is going to be UB sine of my angle, right? So afterwards, it's going to have still the same mass times UBX plus the mass of the bat, and I'm not going to have space for that, times UTX, okay? And we'll have to do the y component somewhere else. But I know everything here. I know everything except for the mass of the bat, or the velocity of the bat. So all I have to do is solve for that, right? And if I do that, what I'm going to get is that the velocity of the bat in the x direction after the collision is the mass of the bat before the collision times the velocity of the bat before the collision, or I'm sorry, the ball, plus the mass of the bat before times the velocity of the bat before, minus the mass of the ball times the velocity of the ball in the x direction but after the collision, all divided by the mass of the bat. Okay?
Professor Nelson, where did all that come from? Did it come from the
This,
momentum initial? Yeah, that whole equation.
this all came from this equation. This is the x component of that equation.
But from the momentum initial?
Well, this is, so these two terms are, so this term right here, put in a box, is that term, right? The x component of that term. This term is this guy, right? It's the x component of that guy. And the same thing's true for this term and this term, right? They're just the x components of that guy and that guy. I just
Okay.
went through each of the terms in my conservation of momentum statement, and I grabbed all their x components. Okay? And that
Okay.
allowed me to write out this thing, which then I solved for the one piece I didn't know. Okay?
Because it's hard to see. It helps when you explain it like that.
Okay, great. Okay, so now we just have to do the same thing for the y components, right? We have to go back through and identify all the y components. So let me actually just scoot this paper down a little bit. Let me see if I can arrange this so you can see both. Okay, so again, I'm going to walk through for the y components of that equation, right? Okay, so the momentum of the bat initially, its y component was 0, right? Because the bat wasn't moving vertically initially, or the ball wasn't moving. I keep messing myself up there. The ball wasn't moving vertically initially. Okay, neither was the bat. It had no y component of momentum initially. Okay, but now I come over here. The ball does have a y component, right? I figured out previously that y component is just the mass of the ball times the velocity of the ball in the y direction, okay? And I can already see that that means I must have a component of my bat's momentum in the y direction, because this isn't 0 and this is all 0 over here. So I better have a term over here for the bat. So that's just going to be the mass of the bat times the velocity of the bat after the collision in the y direction. Okay? And again, all I have to do is solve for that. So I end up with the velocity of the bat after the collision in the y direction is just negative the mass of the bat, the ball, times the velocity of the ball in the y direction after the collision, divided by the mass of the bat. Okay, so here's my solution. You've got the x component and the y component. So if we actually go through and put in some numbers, we can actually figure out what these things are, right? So again, I'm going to do this approximately, but you could plug it into Google and figure it out. The mass of the ball is about 1/10 of a kilogram. So I'm going to write that as 0.1. The velocity of the ball is 33, but I'm just going to call it 30, right? The initial mass of the ball, or bat, is about 1 kilogram. And it's also moving at 30 meters per second, but it's moving at negative 30 meters per second. Okay, this one is a little trickier. The mass of the ball didn't change. It's about 0.1. But now I have to figure out what the x component of the final velocity of the ball is. And that one I can't do in my head. So I'm going to come over here and I'm going to plug it into Google. And I'm just going to ask Google really nicely, what is 49 times the cosine of 18 degrees? And Google very nicely tells me that this thing is just, I don't know if you can even see that. This thing is just basically 46.6 meters per second. And this guy, if I want the sine, is about 15.1 meters per second. Okay, so that means that this guy is negative 0.1 times, I'm going to write that as 40. Let's round it to 50. We'll round up. All over the mass of the bat, which again is about 1. So that's approximately 3 minus 30 minus 5 divided by 1, which is about approximately, right? That's approximately, well, that's negative 27 minus 5 is negative 32. So the bat is going to be moving in its same direction it was moving, because remember, it was initially moving in the negative direction, right? So I guessed right. It's going to be moving in the same way it was before, right? It's just going to be moving that way a little bit slower, okay? 32 meters per second instead of 33. We could get a more exact number if we figured this out more carefully, okay? Okay, now let's come down here to the y components. Again, I'm going to use really rough numbers. So this is approximately a tenth times the y component is a 15 divided by 1. So this is approximately going to be 1.5 meters per second. And I lost my negative sign. It's negative, so I'm moving downwards. So what this means is after the ball hits the bat, the bat's motion is going to be almost unchanged, but not quite perfectly unchanged. And we know that because if you've ever hit a bat with a ball, a ball with a bat, you know that you feel it in your hands when you hit the ball, right? You feel a little jerk in your hands. That's because the bat's velocity changed rather abruptly. Not a lot, but you know, a meter per second in each direction is something you would feel. Okay, so let's review this. This problem was just like the one before it. We had a before and after. We had to write out our conservation of momentum statements, but this is where it changed. Now we had to worry about components. We had to worry about the x and y components of our momentum. Because momentum is a vector, it can have more than one thing happening at a time. It can have something happening in the x direction and something happening in the y direction. Okay, I'm guessing we're all pretty fried at this point. I know I'm feeling like I've been talking forever because I've been yelling at my internet connection when it's not working. So let me give you just a chance. If you have any questions, anything you want to ask real quick, now's the time. Okay, then let's stop there. And we will call that a class, such as it is. So I hope that was useful. I know the technology is not always the most cooperative thing. We are working on things. I actually, while I was online, the university is actually sending me a different wireless internet connection thing. So we're going to try that, see if it works a little better. It got here while we were doing class, so that's kind of nice. But, not good for today. So what I'd like you to do, this momentum stuff is tricky. It's conceptually hard. If you'll notice, the algebra we had to solve here was cake. We didn't have to do any integrals or derivatives. We didn't get any quadratics. All we had to worry about was doing basic algebra. The hard part on these momentum problems is not solving it. It's figuring out what equation to write down in the first place. And the best way to do that is to practice. So that's what the homework is for. The homework is hopefully going to give you some good experience practicing writing down these momentum equations. So give that a try. As I said, I have office hours immediately after this class. So I'm going to turn the recording off, and then you can ask me more questions all you want. But I'm going to stop there, and we'll call it a class.